All right, so when we talk about doing bonding, one of the bondings is covalent bonding, and that covalent bonding is by the sharing of electrons. Come on. Okay, by the sharing of the electrons. Okay, so normally covalent bonds are formed with the non-metals, and we see here that the driving force generally is the octet rule. Okay, the octet rule is when every atom wants to be like the nearest noble gas or wants to get the 8 electrons in the last shell. So first of all, let's look at how are these, how does the covalent bonding even occur? So covalent bonding, so just imagine that here is this diagram, which is also drawn in your book, but let's just draw this here. So we have, let us say, 2 atoms of hydrogen in a very high excited state. In other words, they are like in a very high energy. And in high energy, these molecules are very far apart. So so these atoms are very far apart. So here is one hydrogen and this is another hydrogen. So a hydrogen and hydrogen internally aspire to be like helium. Helium has 2 electrons in its, 2 electrons, it's 1:2. So helium looks like this and hydrogen looks like this. So hydrogen wants to have electronic configuration like that of helium-2. So how can that happen? So right now, this is at a very high energy state. And this high energy state means that they are, not even talking to each other. They are very, very higher up in the energy profile. Here is the distance, the internuclear distance. So just give me 1 minute. Let me get the actual data. Values. I don't have them with me. Anyways, so this is the internuclear distance. So and in a very high state, they are, the kinetic energy is very high. The motion is very high. So in order to make a bond or in order to look like helium, what they are going to do is they will have to give away some of their energy. So they come close to each other. They come close to each other, but sometimes they come very close. They are very close to each other. So if they are very close, when they come very close, there is repulsion. And that repulsion happens because in the end, they are electrons. Okay, electrons and electrons, negative and negative, are going to repel. Okay, now, again, because they are aspiring to be like helium, so they will try again. So again, they'll come, but now they are coming in such a way that the nucleus of one talks to the nucleus of another. So when that happens, then the negative and the positive, they attract. So negative, in other words, the electrons of this hydrogen talk to the nucleus of this hydrogen, and the electrons of the other hydrogen talk to the nucleus of this hydrogen. Okay, so when the nucleus of one hydrogen atom and the electrons of another hydrogen atom, when they connect, of hydrogen atoms, when they talk to each other, so that means positively charged nucleus and negatively charged electrons are going to be attracted. And that's when the bond is formed. So this bond is so in order to make that bond, again, this has to happen only at a certain optimal distance. Okay, at an optimal distance. It is not supposed to be too close. If they come too close, like we said, this is repulsion. If they are too far apart in the top state, they are too far apart. They're not even talking to each other, too far apart. So there is no attraction, they're not talking, there's no, need to make the bond and so forth. But they give off all this excess energy in order to come close. And in order to make a bond, in order to be a stabilized bond, what happens is that this hydrogen and this hydrogen will be like, will have to, all that energy that is given away doesn't go anywhere. It stays inside the bond. And so that energy is called the bond energy. Bond energy. And this bond energy is what that maintains that attraction, the attraction between the nucleus, that energy that, they liberate, they give off that energy. That energy doesn't go anywhere. It comes and it stations itself, or it comes and it sits in the bonds that maintains that identity of that hydrogen molecule. So what happens is, here you have one hydrogen atom, one electron, and then another hydrogen atom comes and it's bringing its own electron. So what happens? Temporarily, this hydrogen gets to share the electron of this hydrogen. And what happens is that the other hydrogen also gets to share this electron. And so this hydrogen gets 2 electrons, and this hydrogen also gets 2 electrons. Although they are only sharing, 2 electrons are being shared. But at one point of time, they do get to keep 2 electrons. So these 2 electrons that are being shared, they form the single bond. So anytime 2 electrons are involved in sharing, they form single bond. Single bond. Okay, so this is an example of a diatomic molecule. All other molecules, same way, the covalent bonds are formed. So this is an example of a diatomic molecule. Now, diatomic means same type of atoms. Same type of atoms. Okay, now let's look at it. This is the covalent bonding. I forgot to put this here. Covalent bonds. And that covalent bonds are formed by sharing of electrons. Okay, so that's one piece. Next is, let's look at, this is one example where hydrogen is used, H2. Let's look at a scenario where let's say chlorine, Cl2, a scenario with chlorine, that is also a diatomic molecule. So chlorine has 17 valence electrons. Okay, another chlorine also has 17 valence electrons. I mean, not valence electrons, sorry, 17 electrons, 7 valence electrons. So 1s2, 2s2, 2p6, 3s2, and 3p5. 3p5. And 3p5 looks like this. 3s2 is here, 1, 2, 3. Here is the 3s2, and p5 is 1, 2, 3, 4, and 5. Okay, and here you have 1s2, 2s2, 2p6, 3s2, and 3p5. 1, 2, 3. Okay, and here you have 3s2 and 3p5. So these are the orbital diagrams. It's always very important to make the orbital diagrams, even though you may feel it's not needed or whatever. But you see, orbital diagrams help you see how many electrons are unpaired. So the first one, there is 1 unpaired electron, and the second one also 1 unpaired electrons. So when there are 2 unpaired electrons, they are looking to pair. So this is where the overlap occurs. So that's where they're sharing now. So this chlorine gets to keep that electron of the other one, and this one also. So how do you show it in the Lewis structures? So here is this chlorine, another chlorine. So anytime you draw the Lewis structures, you only put the valence electrons. So there are 7 valence electrons here and 7 here. Okay, so that is the Lewis structure of chlorine with its 7 valence electrons. So 1, 2, 3, 4, 5, 6, and 7. The other one is 1, 2, 3, 4, 5, 6, and 7. So 7 valence electron here and 7 here. Now, chlorine is very close. Chlorine 17, very close to which noble gas? Which noble gas? Argon. Very good. And argon has 18. So chlorine wants to be like argon. Okay. So in other words, chlorine wants 8 electrons in its last shell and fulfilled orbitals also. Fulfilled orbitals. Okay. So here is your chlorine now overlapping and, you know, attracting this other electron, and the other chlorine also, you know, is going to overlap and this thing. So basically these are clouds. So this way, this chlorine gets to keep this electron also. So now this chlorine gets one more electron, and now it has 8 electrons in its last shell. So this is the deal with that. And it gets fulfilled. Remember that this electron, when they are overlapping, this electron can come here, and then this electron can come here also. So, you know, they kind of like have more room to move around. So at one point of time, you know, one chlorine will have both the electrons, and another point of time, the other one will have both the electrons, but it's all mutual sharing. So here is this other chlorine also getting one more electron. So plus 1 electron, and you have 8 electrons here. So both the chlorines have their octet met. So that is the octet is met. So that is the octet rule. Octet is met for both of them. And with that 1 electron from each, you know, spending more time in with the other orbitals, then it's, you know, it gets fulfilled also. So that's the fulfilled orbitals also based on that. Okay. So that's the diatomic molecule of chlorine. Now let's look at a scenario with oxygen. Oxygen is O2. Okay. So oxygen situation is same story. Oxygen has 8, 1s2, 2s2, and 2p4. And it looks like P4 is like this. So the other oxygen is 1s2, 2s2, and 2p4. And here you have 2s2 and 2p4 is like this. So we have 2s2, 2s2. Okay. Okay. And then you have 2p4 and 2p4. So 1, 2, 3, and 4. 1, 2, 3, and 4. So how many unpaired electrons do you see? Unpaired electrons. Yeah. So on each, there are 2 unpaired electrons. So then what is going to happen? This one is going to overlap with this one, and this one overlaps with this one. Okay, so that is anytime 4 electrons are overlapping. In that case, we have a double bond. Okay, double bond. And double bond is 2 bonds, 2 single bonds basically. So in this case, chlorine case, it was chlorine and chlorine single bond, only one, you know, this one overlapped. So 2 electrons overlap, and that's a single bond. Okay. And then in this case, there are 4. So let me just write this down here. When 2 electrons, let's put this here in red, 2 electrons make a single bond. 4 electrons make a double bond, and 6 electrons make a triple bond. So we will see that. Okay. So here Now, how to draw the Lewis structure of oxygen? Oxygen Lewis structure is, this is the other. So this is this guy and this guy are placed like this. 1, 2, 3, 4. And the unpaired ones are placed like this. You get that? This is one lone pair or bonded, like the paired. The other one is also paired. And now these guys are looking at each other. It's very important. In chemical kinetics, you must have studied in previous lectures or previous courses that the atoms need to look at each other in order to form the bond. So this and these two are connected or bonded, and these two are bonded. So this is one single bond, another single bond. So 4 electrons overlap. Therefore, double bond is formed. Okay, so that is the Lewis structure of oxygen. So 4 electrons overlap, double bond, and we write it as O2. Okay, now let's look at a scenario with nitrogen. What happens in the case of nitrogen, N2? Now nitrogen is 7. The other nitrogen is also 7. So 1s2, 2s2, and 2p3. 2p3. The other one is 1s2, 2s2, and 2p3. So how does it look like? Here we have 2s2 and 2p3. And here we have 2s2 and 2p3. So we are going to say this 2s2 is this guy, and 2s2 is this one, and 2p3 is 1, 2, 3. 1, 2, 3. Now tell me, how many unpaired electrons you see? 3. 3 unpaired on each. So 3 unpaired electrons. So when these 3 unpaired electrons, so in other words, 6 electrons overlap, or they connect and they form a triple bond. Triple bond. Okay, so this is not a double bond, just a triple bond. Okay, so how does this look like? This and this overlap, this and this one overlaps, this and this one overlaps. So basically, how do you show this? So here is this nitrogen. These two guys are going to be away because they don't need to, they're already paired. These guys are needing to pair. So, obviously, when people are dating or whatever, you go on like dating sites, you put your picture, your profile and whatever, and you want to make friends and so forth. So that's how looking, this guy, this one, and this one. So that's how the networks are formed, bonds are formed. So here is the scenario where 6 electrons are, overlapping. So in other words, if you look at it, this nitrogen gets to keep the 3 electrons for it. It already had 5 electrons in its last shell, plus it gets to keep 3 more. So it becomes what? 8 electrons. The other one also had 5 electrons in the last shell, and it has 3 more electrons. So gets to like share, basically sharing. Sharing is just overlapping. So 8. So each nitrogen has octet, met, and it also gets a full filled orbitals. So remember that if they're sharing, then these guys will spend, but these guys will go and spend some time with these people, this space. In this space, they're going to come and occupy this space also. So each of the orbitals temporarily get filled. So as far as there are the fulfilled orbitals and the octet is met, in other words, 8 electrons each of them get, that's a very happy scenario for every atom. Nitrogen wants to make 3 bonds, nitrogen will make 3 bonds through this. Oxygen, same is the story with the oxygen also. I forgot to put this here. So here you have this oxygen, had 1, 2, 3, 4, 5, 6, but it gets to keep these 2 more electrons. So 6 electrons initially plus 2 more electrons. This oxygen gets 8 electrons. This oxygen similarly gets to keep those 2 electrons. So 6 electrons initially plus gets 2 more to share, then 8 electrons. So the octet of oxygen is also met. Octet is met. And through this overlap, the fulfilled orbitals, the orbitals get fulfilled. Okay, so this is a very stable condition. Okay. All right, so that is the deal with making the single, double, and triple bonds. Now comes a scenario where you have different types of atoms. So that was just the diatomic. Now let's see if, okay, these are the rules. Wait 1 second. I posted them here, so you guys can copy these rules in your somewhere in the handout, but it's very small. So let's see if I can make a bigger one. Okay. Here is a little bit bigger, and okay, that's the best one we can get. Oh, I'm trying to just get it, you know, so it doesn't, so it fits the, because I know some of you make these copies, so. Okay, so these are the rules of drawing the Lewis structures with three or more different types of atoms. Okay, 3 or more different types of atoms. So in that case, how do you draw? What are the rules for drawing the Lewis structures? So I have them here. Like I said, you guys need to copy them in your handouts or in your notes so you don't lose them. And then there is a worksheet also, which you need to do. So look at these first. Okay. Even before we start that, I want to touch base with something that you might have forgotten, but just review this. The bonds that are formed. So, okay, we have group numbers, and now we are just going to look at the bonds. And yes, initially there were charges.
Record, please.
There were charges. Okay, here, important. Group number 1, group 1A, will form only 1 bond. And because these are metals, there's going to be +1 charge. Group 2A will form 2 bonds, and there is going to be +2 charge. Group 3A, 3 bonds, +3 charge. Okay, group 4A will make 4 bonds. Okay, there can be +4 charge, there can be -4 charge. That is if they are transferring electrons. Plus, they can share electrons also. Okay, then comes group 5A. 5A will make 3 bonds, and there is going to be charge -3 if they are losing electrons. Okay, but if they are gaining electrons, that will be -3. But you have, nitrogen and phosphorus here. Nitrogen and phosphorus. Let's see, 1 second. We will do these also here. Okay, 5A is -3, 6A is 2 bonds, -2 charge, 7A is one bond, and that's -1 charge, and 8A will be making no bonds and no charges. But keep in mind here, there is going to be exceptions to the rule. Exceptions. Okay, these are some exceptions. And so what are those exceptions? So here, keep this in mind that these guys are metals. These are metals. So the charges are only formed when these non-metals react with the metals. But we are not talking about the metals here. We are talking about the non-metals. So exceptions. So look in handout. So this is one thing I'm writing this here. Look in the handout, which is on page number 1, 2, 3, 4, page 4, and notes here, and notes below. Okay, so now let's look into this piece. What are the exceptions? So exceptions are here. Exceptions are that CPTIONS. Now, exceptions are, okay, hydrogen, okay, group 1A, right? So it will have one valence electron and it makes one bond. Now we are looking at the covalent bonds, exceptions in covalent bonds, in covalent bonds. So that's simple. That's always that's always going to work. That's when the bonds are made by sharing. You know, when sharing, like the non-metals basically connecting with each other, non-metals and non-metals, when they bond to each other, then what are the scenarios? So those are what we are looking here. Okay, hydrogen is that. Then helium obviously will not make any bonds. Then comes boron. Boron is in group 3A, and this is going to have 3 valence electrons, and this is going to make 3 bonds. Okay, next is carbon. Carbon belongs to group 4A, and this is very important actually. Group 4A, and it will have 4 valence electrons, and you know, when it's sharing electrons, then it will make 4 bonds. 4 types of bonds. It could be double bond, triple bond, combination, you know, those things. Now, in group 4A, another one is silicon. Silicon also is in group 4A, and this has 4 valence electrons, and silicon also, because it's a metalloid. So it can act like a metal and a non-metal, so it will also make 4 bonds. Now pay attention. Problem starts from here. Nitrogen, yes, it belongs to group 5A, and just like we talked about, that 5A has 5 valence electrons. So nitrogen ideally should make 3 bonds. No, sorry, 3 bonds, not 5 bonds, 3 bonds for nitrogen. And that happens. But sometimes there are exceptions even with nitrogen. It can also make 4 bonds also. Okay, but the worst is here, phosphorus. Phosphorus is also in group 5A. It has 5 valence electrons. It can make 3 bonds all the time, yes, but it can also make 5 bonds. Now, in what condition it makes 3 bonds and what conditions it makes 5 bonds, we will look at that. Okay. So I'm going to just put a star here. So you know it that when it's making 3 bonds and when it's making 5 bonds, when that happens, we will look into this. Okay, next is, now these are not given in your book, you know, so it's very important you understand this. Oxygen is in group 6A, and that is 6 valence electrons. Okay, will make 2 bonds all the time. Okay. But sulfur is in group 6A, but sulfur has 6 valence electrons, but sulfur can make 2 bonds. In very special condition, sulfur can make 4 and 6 bonds. And what are those conditions? So I'm telling you guys, these, I don't know why they never give these things in the book. So I'm bringing this from outside so you understand that, because they just give you examples and you're like, oh, why is it making all these 4 bonds now? So we understand why is it doing that. So next comes fluorine. And yes, fluorine, chlorine, bromine, and iodine. These belong to group 7A. They have 7 valence electrons. So yeah, they will only make 1 bond. So the whole driving force is, octet rule. Octet rule. When they are forming they are obeying the octet rule, then they make these 3 bonds, 2 bonds, and in this case 1 bond. But chlorine, bromine, iodine can defy the octet rule. So they can also make 3, 5, and 7 bonds. Okay, so 3, 5, and 7 bonds also. These are the exceptions. Next is the helium, neon, argon, krypton, xenon. No bonds, 0 bonds, and that's fine. Noble gases. Why do they? They have 8 electrons in the last shell. So they are not going to make any bonds. So all these guys that are with the green stars, these are normal conditions when they follow the octet rule, or or basically, wait a minute. Let me just do this here. This guy and this guy is different. This is, and this one. These two are different. Okay. Now comes the xenon. Xenon, you can make xenon make bonds. So it can make 2, 4, and 6 bonds. Okay. So what does this mean? Red means defying octet, and green means obeying octet. And what conditions is that? In what conditions they will obey octet? Okay, they obey octet. When the green star means they obey octet, they follow the octet rule. When when these atoms are bonded to another atom that has lower electronegativity. Electronegativity. Okay, electronegativity is En. Okay, so that's one piece. Whenever they are connected to an atom with a lower electronegativity, then yes, they will make all these usual bonds. But when they are, they defy all these ones, when they are red star, means they defy octet, means that they do not follow the octet rule. And when does that happen? That happens when they are bonded to another atom, that has higher electronegativity. Okay, higher electronegativity. Okay, such as generally, these are in the case of like polyatomic ions. Okay, so when they're connected to negativity. Okay, such as, for example, with oxygens, like for example, phosphorus Look at this phosphorus. Phosphorus, or which one is the first one? Yeah, phosphorus. Phosphorus, when it combines with phosphorus with hydrogen. So in this case, phosphorus electronegativity is higher than that of hydrogen. Hydrogen has a lower electronegativity. Okay, so in that case, then phosphorus will make only 3 bonds. It's following the octet rule. So it will make a molecule PH3. This is one piece. But on the other hand, these are the examples. Okay, when phosphorus combines with oxygen, so in this case, the electronegativity of phosphorus is lower than that of the electronegativity of oxygen. So in this case, it can make 5 bonds. Okay, so in that case, we will have PO4, 3 negative. PO4, yeah, 3 negative. Phosphate ion. So this is phosphine molecule, and this guy is the phosphate ion. So phosphate ions is going to be 5 bonds. Okay. Similarly, look at this. Another example. Example 1, example 2. Look at this. You have sulfur with hydrogen. When sulfur mixes with hydrogen, sulfur electronegativity is more than the electronegativity of hydrogen. So in that case, sulfur will make 2 bonds. Sulfur is in group 6A, 2 bonds. So the molecule formed is H2S. That is, what is the name of this molecule? Hydrogen sulfide. Okay. All right. Next is you have sulfur with oxygen. Okay. So oxygen, so sulfur in comparison to oxygen now is bonded to oxygen, which is higher electronegativity. So sulfur can make 4 and 6 bonds. Like for example, sulfate SO4 minus 2. So here this is making 6 bonds. So you see that? So this is an example of polyatomic ion. So polyatomic ions, you know, they're going to make more, they expand their capabilities. So this is also a polyatomic ion. All right. Okay. So now comes another scenario, the last one. Hydrogen and boron will never follow the octet. So just keep it here that these guys, hydrogen and boron, hydrogen and boron do not, or I'll just write down here, never, because it makes sense. How many electrons does hydrogen have? Only 1. And octet, we are looking at 8 electrons. So, you know, why wouldn't hydrogen need to have 8 more electrons? I mean, it doesn't matter. So for hydrogen and boron has 5 electrons. So, you know, it's not feasible for boron to have, you know, 3 more. So it just goes through, you know, it's different type of bonding with boron. There's something called hybridization, which we'll study later. So boron goes through the process of hybridization. Carbon also goes through the hybridization process. So we will look into that later. So anyways, so never follow the octet. So keep that in mind. All right. Now, any questions so far? Any questions on this? Okay, let's just do this little review here from your handout. If you look in the handout, there are here. Okay, you will see now. How do you know which one is a more electronegative, which one is less electronegative? In general, these are the trends in the periodic table. So you see this ionization energy, this relates to electron affinity, and this also relates to electronegativity. So if you want, you can make a note here of make a note here, make a note of where the ionization energy is written, that the electronegativity in also increases as you go from left to right in the periodic table, and the electron affinity also increases. So this is one piece, right? And as you go down, the electronegativity decreases and the electron affinity also decreases. Okay, from this side. So that's one thing when you go move from left to right. So that means all the non-metals will have very high electronegativity and the electron affinity. So if you were to compare hydrogen's electronegativity with that of helium, hydrogen is less electronegative than helium, but you know, that's just immaterial. But look at that carbon versus fluorine. Fluorine will be more electronegative. Similarly, nitrogen versus chlorine. Chlorine is more electronegative than nitrogen. Okay. Similarly, nitrogen and oxygen. Oxygen is more electronegative than nitrogen. Phosphorus versus sulfur. Sulfur is more electronegative than phosphorus. Now, electronegativity, like I said, it's decreasing when you move from top down, or the electron affinity is decreasing. So what's happening? That in the same column, when you move from top down, let's say oxygen and sulfur. So oxygen has a higher electronegativity than sulfur. Okay. So keep that in mind. Chlorine has a higher electronegativity than iodine. So top down, it's also decreasing. So keep that in mind. Okay, that's one piece. Next thing is, if you look at it, another, so the same thing that we discussed about the covalent bonds, you know, all that has been summarized here. So pay attention that the ones that are given in the brackets right here, these are those when they are connected to more electronegative atoms. Similarly here, sulfur more electronegative atom, it can make 4 and 6 bonds. Chlorine, more electronegative, actually it can make 7 bonds also. And then similarly, you go to, you know, iodine and all this, 3, 5, and 7 bonds they can make. So this is one piece that's in your handout, so you can miss it. So I would just say that write down here, if you want to, what is it, you know, in the brackets and what is it without the brackets. Something I already put for you in the notes. Now look at this. Here, right here. These are the values of the electronegativities. These have been identified. The electronegativity has been measured on the Linus Pauling scale. So if you look at this electronegativity values, so which one is the highest electronegativity? Which one? Fluorine, very good. So fluorine has the highest, and which one has the lowest? Lowest. Look carefully. Cesium, very good. All right, so this means the electronegativity increases, means the ability to pull the electrons increases. Fluorine is going to pull the electrons with a greater force than oxygen. Oxygen will pull the electrons with greater force than nitrogen, and so forth. Okay. Similarly, chlorine will pull the electrons with greater force than bromine. So 3.0 is bigger than 2.8. You see that? Sulfur 2.5, selenium 2.4. So sulfur more, you know, pull of the electrons than selenium. So this is one thing. Now, the atoms that have the capability of pulling the electrons towards themselves, they are going to generate a polarity in the molecule. So if there are two different atoms in a molecule, a slight negative charge develops like this, and a positive charge develops. So here's the thing, because remember, these covalent bonds are formed by sharing. So if there are the same atoms, so the pull of the electrons is going to be the same. So it cancels out, no matter how electronegative the atom is, But if there are two atoms connected or bonded and both of them are pulling the electrons with the same force, then that means the electrons are being shared equally. So that becomes a non-polar covalent bond. Okay. On the other hand, when you have the electrons shared unequally, in other words, one electron, the one atom is more electronegative than the other one. So in that case, a slight negative charge is formed on one side of the molecule and a slight positive charge is formed on the other side of the molecule. Then what happens? Then in that case, a polarity, this is unequal sharing of the electrons, and you get a polar covalent bond. Okay. Now, ionic bonds are formed if there is a complete separation of charge. So complete separation of charge forms two separate entities. These are two separate entities. One is a negatively charged species, the anion, and the other is positively charged cation. Cation is always have a smaller size than the anions. That's one thing. So in that case, the electrons are transferred. That's an ionic bond. Now look at this. Look at this difference in the electronegativity. When you subtract the electronegativities of each of these, you know, when a bond is formed, if the difference in the electronegativity is from 0 to 0.4, then it is non-polar covalent. When it is from 0.4 to 1.8, then it is polar. And if it is above 1.8, then it is ionic. Okay. So that's the story with these guys. And then there is a net polarity. Net polarity is equal pull on both the sides. So look at this. Carbon is in the middle, oxygens, two oxygens on the same side. So these are the dipoles, right? Oxygens on the same side. Oxygens, one oxygen is pulling the electron cloud with one force. The other oxygen is also pulling the electron cloud with the same force. And so it cancels out. So the molecule becomes non-polar. Yeah.
So is that saying that if it's non-polar covalent, that means like all diatomic molecules, right?
Yeah, will be non-polar. Yes, yes. Yeah, very good. Very good thought. Good thought. Good, very good, Keith. Good thought. I was going to bring that one up. Okay, then look at these carbon with 4 chlorines pulling the electron clouds towards itself. On the same chlorine atoms. Chlorine is highly electronegative. Look at this. Chlorine electronegativity is 3.0. Carbon is 2.5, right? So when the pull 3.0 minus 2.5 is 0.5, 0.5, and that falls under the polar covalent bond category. Okay, between 0.4, so it's above 0.4, so it's 0.5. So yes, this carbon chlorine bond is very polar, but it's the same pull on all the 4 sides, so it all cancels out. So the whole molecule becomes non-polar. All right, same is the case. Look at this, hydrogen and chlorine. Chlorine more electronegative than hydrogen. Chlorine electronegativity 3.0. Hydrogen electronegativity is 2.1. So 3.0 minus 2.1 falls in the category of polar covalent. So there is a, like, you know, charge so that becomes the, you know, this is a polar molecule. Okay. So if just keep this in mind, that if there is a lone pair on the molecule, on the central atom, if there is a lone pair, always going to be polar. If there is a lone pair right here, always going to be polar. If there is a charge in a molecule, polar. Okay. So now let's look at, so all this now, I covered the basics. So now we are going to look at the, let me put a note here that in handout, refer, so for doing all these, you know, refer to the handout for what? Now for number 1, and that is on page 4. Page 4. These are the covalent bonds in nonmetals. Covalent bonds in nonmetals. So this is one. Next is on page, before that, yeah. Just, you know, electronegativity increases, all those things. That can also be seen. It's better here on page what page is that? On page 8. Page 8, you have, page 8, you have the electronegativity like values, electronegativity values. So, you know, anytime you are in the classroom, you should always have your handout with you, electronegativity values, so you can just, you know, calculate. Then you are going to here look at on the same thing on page, this is table 6.4 on page 8, table 6.4, and this table 6.14, sorry, 6.14 talks about the polar, non-polar, and ionic bonds. Okay, ionic bonds. And then comes the fourth is the net polarity in the molecule. Net polarity. And then same thing on page 8 is the table, same thing, just net polarity. So you get an idea of, you know, what it means. Okay, besides that, we are also going to cover the, okay, on page, we are also going to look at the shapes. So let's look at those also. 7, 8, 9. Then on page 9, page 9, there is a table 6.16, 6.16, that is in general, that is for the shapes. Okay, shapes for this. All right. And there are more shapes also. This is just general shapes, you know, but we are going to take more shapes for the table. Oh, this always happens. Okay, besides that, you know, on you also have, there is also, what is it called? I also have a worksheet that is on, which talks about the Lewis structures with the tables on it, which has more complex, you know, and that you would need that. Where is that? 9. Oh, I'm in the wrong. Anyways, let's just keep this thing. I will reach to that one when we come. So let's do this now. Okay, let's start making some of the molecules, the Lewis structures of carbon tetrachloride. Okay, so if there is 1 chlorine and 4 chlorines and 1 carbon. So here are the rules. And these rules, like I said, you should write those down. But the rules are: number 1, first, always start with counting the total number of valence electrons, always. Next is you're going to, if there are 3 or more atoms, you're going to identify the central atom. So how do you identify the central atom? You're going to look at the one with the lower electronegativity, that goes in the center, but not always. Okay, so not always. Yeah, we prefer the one with the lower electronegativity to be in the middle, but we are also going to look at the one that has the maximum capacity to make the bonds. So that one takes the priority. So even though it may have a lower electronegativity, but if it is able to make more bonds, then it gets to be in the middle. Next is you place the central atom in the middle, and then you combine the other atoms from the outside of the central atom, and then you connect the central atom with the outer atoms using a single bond. So remember that every single bond uses 2 electrons. So you count how many single bonds you made times 2. Okay. Next is how many electrons are left now. So you're going to take all the electrons that are used in making the single bonds minus that from the total number of bonds. So any leftover electrons are placed on the central atom. Okay. And no, sorry, any leftover electrons are placed on the outer atoms. First of all, to cover the octet, okay? And then the remaining ones go on the central atom. And then you check, you have to always check. You check whether the octet of every atom is met or not. If it follows, if that atom follows the octet rule. Remember, hydrogen doesn't follow, so you don't have to like force octet on that. So if that atom follows, boron doesn't follow, follows the octet. Okay. Next is you see of the outer atoms if their octet is met, and then you look at the central atom if the octet of the central atom is met or not. And then remember that sometimes the central atoms, there can be exceptions. Exceptions could be the ones that defy the octet, and those are, we already looked at it. It could be phosphorus can defy the octet, sulfur can defy the octet, chlorine can defy the octet, bromine can defy the octet, iodine and xenon can defy the octet. These guys can, not all the time, can defy the octet. So octet rule may apply and may not apply. Next thing, you're going to see if the need to make the bond, that is satisfied or not. Octet is one thing. If the octet is met, that's good. But you also have to see, are they happy? They want to make the bonds. So that need to make the bond is satisfied or not. And if not, then you do the rearrangement. Rearrangement means that in order to make a bond, you have to still get to the octet. That means that you are going to, create, like involve the lone pairs or move the lone pair to make double bond. Okay, got it? All right, let's do it now. Okay, now we are going to look at carbon tetrachloride. So first is total number of valence electrons. Total number of valence electrons. Carbon, 1 carbon, 4 chlorines. Okay, 1 carbon and 4 chlorines. 1 carbon has 4 electrons. Chlorines have 7 electrons. So we have 4 coming from carbon and 7, what is that? 7 for 28 coming from chlorine. So how many total? 32 electrons, right? Yeah. So that's one piece. That's the first step. Next, what's the second step? Central atom. All the time, do that. Central atom. Identify the central atom. So you're going to see that will it be carbon versus chlorine. So first thing, electronegativity of carbon. What is that? You guys tell me from your handouts. Electronegativity of carbon and electronegativity of chlorine. Okay. Very good. So which one is more? Fluorine. So that means which one is going to be in the middle? The one with the lesser electronegativity wins. So the central atom is going to be the one that has a lesser. Besides that, we also have to check another thing, that the bonds. So carbon, when it is connected to chlorine, right? Carbon can only make a maximum of how many bonds? 4 bonds. And chlorine is connected to carbon, which is a lower electronegativity. So in that case, chlorine will only make 1 bond. Chlorine is not connected to oxygen. Keep that in mind. Yeah, chlorine can make 3, 5, and 7 bonds. Only if chlorine is connected to oxygen or to other higher, like fluorine, other higher electronegativity atom, then chlorine will make 3, 5, and 7 bonds. But chlorine is connected to carbon, a lower electronegativity, only 1 bond. So which one gets in the middle now? Carbon gets to be in the center. Okay, now you place carbon in the center. Place carbon in the center and put the chlorines outside. Okay, put the chlorines outside. Then you connect them. with the single bond. So 1, 2, 3, and 4. How many electrons did you use? How many did you use? 8. Very good. So 1, 2, 3, 4, 5, 6, 7, and 8. 8 electrons used in single bond. Okay. So how many were total? 32. So 32 total minus total valence electrons minus the 8 that got used in single bonds. How many left? 24. So where are you going to put these 24 electrons? On the outer atoms first. These go on the outer atoms. And so here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. All the electrons got used up in making the, just one second, in making the, I have your, in making these bonds. So is it a stable bond? You're going to check. So check now. What are you checking here? What will you check? Remember the rules? I'm going to just put here. You guys tell me. Where is it? So what will you check? Yeah. Come on, guys, tell me, what are you going to check? What is written on the board? In the class here. Come on. Check for what? The people see, for some reason, I think we should, in future, we should have classes just online for lectures and then just come in the lab. And that's what's actually happening. Next semester, that's what I'm doing. Lecture online and just come to the lab. That's it. But test is going to be in the lab. So that, now more people communicate through these, Zoom meetings, but you guys are quiet. Come on, tell me now. What is, see, one thing, one rule of the thumb. Anytime I put something in red, that means it's like super, super, super important. So what do you see here? What is this? Tell me, what is underlined?
We can't see anything.
Oh,
Yeah, that's right.
oh, how did that happen? But it's weird. How did that happen? Because these folks are seeing something else. And you guys are seeing something else. Okay, anyways. Okay, that is why. Okay, anyways, but okay, you guys are seeing this piece, I see. Okay. Oh, I see. Sorry about that. Okay. Okay, now tell me. Octet, very good. So you check for the octet, and the second thing is you check for the need to make the bond. That is the most important thing. Need to make the bond. And if that need is not satisfied, then there is always a rearrangement. Okay. Now, we are going to look here that, look here, is this. Now tell me. Carbons, look at carbon. 1, 2, 3, 4, 5, 6, 7, 8. So carbon is carbons has octet met. Okay, and each of the chlorines, 1, 2, 3, 4, 5, 6, and then 7, 8. These are also shared. Okay, these are also shared by chlorine. This is also shared. Each of these two are shared, and chlorine has these 6. So every atom has its octet met. So this is where you just stop. Okay, you stop here, and 8 electrons on the chlorines also. And carbon wants to make 4 bonds. Carbon is in group 4A, right? Group 4A, 4 bonds. And chlorine is in, 1 bond. Chlorine is in group 7A. So 7A, will make 1 bond, and so this is what it is. Okay. Now, included here, I'm also going to include the shapes and polarity. We are going to also look at the shapes and polarity. So everything is also, so the way the whole thing is given in your book is all scattered. So, because that's the way the chapter has to be written, but I have done this in the, in this fashion that we, we'll, for every example, we will look at it. Okay, here, polarity, first of all, polarity. Now, you guys go and look in the handout and tell me, look at the electronegativity of carbon and chlorine, and tell me whether carbon-chlorine bond is polar or non-polar. Polar. So what is the difference in electronegativity? So carbon, so chlorine is 3.0 and carbon is 2.5. So difference in electronegativity is subtraction. Okay. Minus. So difference delta En is equal to 0.5, and that is polar bond. Okay, got it? So now pay attention to this. Here is carbon, chlorine, 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 and chlorine. Each of them will be pulling the electron clouds towards itself. So in other words, what's happening is that this is what's happening. The electrons are spending more time towards chlorine. So if you were to do the heat maps means that if you were to put this like, they put them in like thermal maps or heat maps, just to get the heat in a molecule, where are the electrons spending more time? So they see that the edges are more hot, but the middle part is very cold. So the electrons are not spending the time much with the carbon. So that side is the cooler side. So this is hot region in this molecule, and this is cool. Okay, and that means the electrons are spending more time towards chlorine. So therefore, each of the chlorine will have a delta negative charge because of that. Since these are polar bonds, this is what the polar bond means. Polar means polarity, means unequal sharing of electrons. Unequal sharing of electrons. And that unequal sharing of electrons is what makes this molecule like each of the bonds to be polar. Okay, so that means that this chlorine is pulling the electron clouds towards itself. You show it like this. This chlorine is pulling the electron clouds towards itself. This chlorine is pulling the electron clouds towards itself, and this chlorine is also pulling the electron clouds towards itself. So there is equal pull. So there, each of the chlorines, let me put this here, each chlorine pulls electron clouds with equal force, because they're all chlorines, with equal force. Therefore, the effect of the pull cancels out. So what happens then? The molecule becomes overall polarity is 0. Overall polarity also means net polarity. Net polarity is equal to 0. So therefore, Cl4 molecule is non-polar. So even though it has, even though every bond is polar, but overall molecule is non-polar. Okay. Now we are going to do the shapes. So give me 1 minute. That's what I had it on the screen, but let's see if this one can share. 1 second. How do I? And 1 minute. And this is share the screen. Here. Is that happening here also? It's not happening. So I don't know how this works. Stop sharing. Okay, so I'll have to do it the other way around. Okay. All right, just give me 1 minute here. So go to modules. Okay, this is, the table on the shapes that you have in your handout is like from your previous, rudimentary courses, previous courses. But the table that now you are going to use is the little bit more advanced. More advanced. And that advanced is this piece right here. Bonding. Okay. Loose structure. Okay, here it is. All right, so this is the rules regarding the Lewis structure are also printed in the worksheet. Okay, guys, you see this now? Yeah. Okay, so this is what we are going to do now here. Now pay attention, everyone. What does this mean? A means, A stands for central atom. Central atom. This is the worksheet you will use. Okay. X stands for outer atoms. Outer atoms. Okay. And E stands for lone pair on the central atom. Lone pair on central atom. Okay. And then all these shapes are with respect to what is happening around the central atom. That is why the central atom is so important. Okay, central atom. All right, guys. All right. Now let's look at this. If there is only one atom and it's connected to, like one atom is connected to two other atoms, then the shape is linear, like a line, like a straight line. If the central atom is connected to three other outer atoms, okay, that means there are total number of electron groups. Electron groups means that the bonded, like the bonding, the total number of electron groups means you would need it for the next one. So electron group stands for the electron groups are, how do I put this here? The single bond, double bond, and triple bond, and lone pair. All of them constitute like one electron group. So if there is only one single bond, double bond, triple bond, that is going to be one electron group. if there are two, like two double bonds, then two electron groups. So anyway, so whether it's a single bond, double bond, triple bond, it is still considered to be one electron group. Okay, so that's one thing. Number of bonding electron groups means, in other words, one number of bonding atoms. Number of non-bonding atoms. So non-bonding atoms are the lone pairs. And the bonding atoms are just, this is the bonding electron groups means the bonded atoms. Then the electron group geometry is internally, what is the shape? That is the internal shape. Molecular geometry is the outer shape, and then the bond angle. Okay, so here we have AX2E1. A stands for the central atom. X2 are the two outer atoms. E1 means there's only one lone pair on the central atom. Okay, if you have similarly AX3E1, A is the central atom, X3 are the three outer atoms, and E1 are the lone pairs on the central atom. Here, look at this. A is the central atom, X2, there are two outer atoms, and E2 is there are two lone pairs on the central atom. So with that said, look at the shapes. There is a trigonal planar, tetrahedral, bent, and then octahedral, all that square planar. So we will study this more, when you do next chapter, which is important chapter. So here, let's look at now the shape. Now for the shape, I would say that shape means refer to the Lewis, this is the table, refer to the table in Lewis structure worksheet. And that table, you can actually print it out and keep it with you. Okay, Lewis structure worksheet. Okay, guys. So we are now looking at this molecule CCl4, which looks like this. So this is A, stands for carbon. X, there are 4 chlorines. So this is AX4 type. Okay, and look at the table. It's very easy now. Oh God, why does it just keeps on? AX4 right here, AX4. You see that in this table? You see everyone, AX4? AX4, 4 electron groups. 4 electron groups means there are 4 single bonds. And how many chlorine atoms are there? 4. Is there a lone pair on carbon? No. So the shape, internally, the shape is tetrahedral. And externally, it also looks like the tetrahedral. And the angles are 109.5. So this means that this is going to look like a chair. So this is the back of the chair. Sorry, this is the back of the chair. This is the side, like at the back. Why do I keep writing chlorine? This is carbon. This is on the side. This is in front, like a wedge shape. This is in front, and this is in the, like at the back. And this is on the top. So like a 3-legged chair. And that 3-legged chair, see, once you identify that, once you draw the right structure, and then you just have to look at the table, and then whatever it is, they just copy. That's very simple. So this is the tetrahedral shape. Tetrahedral. So the electron group geometry means internally. If you were to enter the molecule internally, the shape would be, so this is an internal shape. And molecular geometry or molecular, this is the shape from outside. So external shape. external shape. So according to the valence shell electron pair repulsion theory, each of these chlorines, you know, they try to spread as far away as possible. Because in the end, remember, these are electron groups. There are 4 electron groups. 4 electron groups relate to 4 single bonds. Okay, and so they don't like each other. It can be very, very like very cluttered, very squished, and they repel each other. So the only way they can be as far away from each other and still be connected to carbon is at 109.5 degrees. Okay, so this is the repulsion. There is a repulsion in lone pairs and bonded atoms. So that is what this theory means. So the only way they can manage is if they are as far away from each other as possible. Okay. So that's one thing. Now let's look at an example of, you know, like I will do it for, let's do for H2S, SO2 and SO4. Or actually, I have a video on this. So this you can see on the video why it happens. Let's do for phosphorus. P, H3 and PO4, 3 negatives. Let's do that. Because the other ones you can see in the videos. Okay, so for phosphorus. So so let's look at total first one for pH3. So there is 1 phosphorus, there are 3 hydrogens, and phosphorus is in group 5, 5 valence electrons, hydrogens group 1A, 1 electron. So we are looking to place 5 and 3, that's 8 electrons. Phosphorus and hydrogen. Phosphorus makes 3 bonds and hydrogen only makes 1 bond. Phosphorus electronegativity is higher than the electronegativity of hydrogen. But remember, phosphorus makes more bonds, so phosphorus makes more bonds. So therefore, phosphorus B is in the center. Okay, now here we have put the phosphorus in the middle and you put hydrogens on 3 sides. Okay, 3 sides like that. And you connect it. So how many did we use? 1, 2, 3, 4, and 5, 6. So 6 electrons used in making single bonds. Used in making single bonds. And how many did we have initially? 8. So 8 electrons minus 6 electrons, 2 electrons left. Where are you going to place these 2 electrons?
No.
Outer, because the rule says outer. That's a common mistake students make. Remember the deal with hydrogen. What is that?
Oh, it doesn't fall off.
Very good. Hydrogen does not, again, look at that red color. Hydrogen does not follow the octet rule. Okay. So where are the 2 electrons going to go now? Where are the 2 electrons going to go? Very good. Phosphorus. Therefore, 2 electrons are placed on phosphorus because phosphorus is following the octet rule. Phosphorus can defy the octet rule, but it's following the octet rule also. You see, that's why chemistry is hard, because these atoms, they just do their own things, you know. So anyway, so here we have this hydrogen wanting to look like helium, and it wants to have 2 electrons. So this hydrogen is happy. He has the 2 electrons. This hydrogen is also very happy. He's having 2 electrons. He's sharing in the end. This hydrogen is also very happy. And look at phosphorus now. Phosphorus has 2 electrons on the top, 2, 3, 4, 5, 6, 7, 8. So the phosphorus is following the octet, and so it has 8 electrons on the phosphorus, and the hydrogen, you know, is looking like helium. So hydrogen is also very happy. And phosphorus is also very happy. Phosphorus, now you're going to check. What will you check? Yes, octet we check. Yeah, octet of phosphorus is met. What else is we are going to check? Hydrogen, you know, looking like equivalent to helium, the noble gas configuration. Right? So hydrogen is also happy. What else? We check. Bonds. How many bonds does phosphorus make? Group 5A, how many bonds? 3, very good. So phosphorus is making 3 bonds. So super happy. So that is also hydrogen. How many bonds does hydrogen make? Only 1. So hydrogen is also happy. You see that? So that's the Lewis structure. It's very important to check. Okay, now comes another thing. Now we have phosphorus. Now we are going to look at the shapes and the polarity. So first of all, the polarity. Remember, anytime I told you polarity. Polarity is anytime you have a lone pair on central atom. Lone pair on central atom. What does that become? Polar. Just close your eyes. Just look at your Lewis structure. Lone pair on the central atom. Don't even think too much. This is always going to be a polar molecule. Okay. Now let's look at the shape. Now back to for the shape, look at the table. Table in worksheet. I mean, I have put it as a rules, you know, it's not just a worksheet, it's the rules also. Worksheet that is stating the rules for the Lewis structure. Okay. All right. So what type of shape? Look at always, if you start with the type, you're never going to go wrong. So we have PH3. Okay, and we know that on phosphorus, there is a lone pair on the, so look at the electron groups. You need to look at the electron groups because you would need it for the hybridization. So get used to it. Electron groups. Three bonded atoms, and there is one lone pair. One single bond, 3 single bonds, and 1 lone pair. So there are 4 electron groups. You guys need to get this, guys, the electron groups, because you would need this for hybridization. Lewis structures, very important. Okay, so we have 1 lone pair. This lone pair is also called a non-bonding electrons. Lone pair is also called non-bonding electrons. And there are 3 bonded atoms, 3 bonded atoms, right? So there are 4 electron groups. So let's look at this sheet. And we have 1 lone pair here. Look at this. AX3E1. You agree with that? So A is the phosphorus, X3 is the hydrogens, and E1 is the lone pair on the phosphorus. Okay, so just the rest is easy. So important is if you identify that, then you're good. So just it relates to total number of electron groups are 4 that we have, 1 lone pair and 3 bonded atoms. And so here is, sorry, yeah. And then this is the 3. 3 stands for the number of bonded electron groups. Electron groups means bonded. Bonded means like the ones that are bonded to phosphorus. So the 3 hydrogens, 1 lone pair, shape is tetrahedral, but that's internally. Outside is trigonal pyramid. So like a pyramid, okay? And that is, so here it is like a pyramid. So lone pair on the top, internally is the phosphorus, outside at the base of the pyramid are these hydrogens. So we will have a system like this. So like that. Okay, so like this. So it is trigonal. Trigonal means 3 parts, pyramid. Like a pyramid. Okay, that's the shape. So you won't go wrong if you can identify the type. So it is A X3 E1. A is phosphorus, X3 is hydrogens, and E1 is the lone pair or bonded, non-bonded electrons. Okay. And last but not the least is the phosphate ion, and that's where the resonance is going to be. So we covered quite a bit of examples here. Carbon tetrachloride. Now we are doing the pH3, and now we will do PO4. PO4 minus 2. Okay, let's do this. And then here I'm also going to do the formal charges also. Formal charges and resonance. Okay, so here we have phosphorus, 1 phosphorus, 4 oxygens, and 2 electrons. 1 phosphorus is bringing in 5 electrons, and each oxygen is bringing 6 electrons. So we have 5 electrons from phosphorus, and we have 6 fours are 24 electrons coming from oxygen, and then we have 2 more electrons. So this becomes what, 9? Did I get this right? No, sorry, this would be, wait, sorry. This is for PO3. This is PO4, sorry, PO4 minus 3. PO4 minus 3, yeah. PO4 minus 3, okay. So this is 3 electrons, not 2. So fix that, please. 3 electrons, 3 electrons. Now we have 32 electrons. Okay. Now that's one piece. These are the total valence electrons. Okay. Next is identifying the central atom. So central atom. So here we see phosphorus has a lower electronegativity than oxygen. So from the table, now you already know from that handout table, we will have the phosphorus electronegativity is 2.1, oxygen is 3.5. So just so you know, it's 2.1. So it has a lower electronegativity. So that's phosphorus. Besides that, oxygen makes only 2 bonds, whereas phosphorus will make 3 and 5 bonds, and oxygen can only make 2 bonds. Okay, so phosphorus is in the center. It's very important you follow this. Next is you put the phosphorus in the middle and you connect the oxygens. See how I'm putting them not at 90 degree, but at like one like the tetrahedral. Okay, next is you connect them with the single bonds. Now, single bonds means you used 1, 2, 3, 4, 5, 6, 7, 8 electrons. So 8 electrons used in single bonds with oxygen. Okay, and you had 32 electrons total. So 32 minus 8 is what? 24 electrons left. So those 24 electrons are going to be now placed on the oxygens outside. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So all 24 electrons have been used up, right? So now you are going to check. So check for the, first of all, the octet of oxygen and phosphorus. Remember that phosphorus can defy the octet. So it's not necessary for phosphorus to follow the octet. And why? Because when phosphorus bonds with oxygen. So very important here. Okay. So one, look at the octet. Oxygens, each of the octets are met. Okay, oxygen's octets are met. If you look at it, so oxygen's octet is met. And for that matter, even the octet of phosphorus is also met. So these guys are okay, but something else is not met. The need to make the bonds. Is it met or not? Oxygen will be very happy if it makes 2 bonds. And phosphorus can make 3 bonds, but phosphorus can also make 5 bonds. So it can extend its capability or its capacity to make bond. And why that happens, I've explained it in the video. It's not like you can, there's no end in chemistry. You can keep going on and on and on. But, we have only certain time period, certain time, so, okay, anyway, so what is going to happen? Phosphorus wants to make 3 bonds, but here phosphorus is making 4 bonds, but phosphorus can make 5 bonds when it connects with oxygen. And oxygen wants to make 2 bonds. So oxygen is very unhappy because it is unable to make the bonds. And phosphorus would be happier if it can make 5 bonds. Okay, so none of them is in a happy condition. So what is going to happen? Rearrangement. Rearrangement. Okay, now let's look at what the rearrangement is. So you have to I'm going to just, so there are no. Okay, so here. Now we have a scenario. I'm going to just now phosphorus, oxygen, this oxygen, this oxygen, and this oxygen. And 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. Now what happens is that every oxygen will say, okay, we need to take turn. Phosphorus has a capacity to make only 5 bonds. So it can't go any further. So an oxygen wants to make 2 bonds. So what is going to happen? One of the oxygen lends its lone pair. And so now we have this scenario where phosphorus makes double bonds with this oxygen. This oxygen is very happy. Octet is met and it's making the double bonds. Okay. And now these guys that are still containing single bonds, fine, their octets is met, but they prefer to have 2 bonds. So what are they going to do? They are the ones who are going to carry that negative charge. All right. Then they say, hey, we need to be fair and we need to take turns. So this guy is going to say, now it's my turn to make the bonds. Sorry. My turn to make bonds. So it lends the charge comes here and this bond breaks, and we have a structure which looks like this. So phosphorus, oxygen. So you see how double bond is basically now rotating. So now this guy gets to keep the double bond, and the others two are waiting for their turns. So they all take turns to hold a charge and to make the bond. So now this one bears the charge, these ones are waiting. So now comes another scenario where this one comes to make the double bond, this one will have to deal with the charge. So now we have phosphorus. This one's still holding its negative charge. This one is now getting a negative charge. And this guy is making a double bond. Okay, and this one is waiting for its turn. So the charges also rotate internally. Okay, and now this one gets to make the double bond, and this charge, this one has to deal with the charge. So now we have a molecule where phosphorus, this one is holding a negative charge. This one is holding a negative charge. This one gets a negative charge. And this one is now making a double bond. So now we have, negative here, negative here, negative here. So you see how the thing keeps rotating, you know. So all these are the resonating structures. So now after that goes here and so forth. Okay, so these are called, this phenomena is called resonance. Resonance is, and these are all resonating structures, resonating structures. So a question of, you know, on these is going to be on the test. So basically this is delocalization of electrons or charges of double bond, sorry, not electrons, but double bonds, delocalization of double bond. So double bonds, you know, this rotate, okay, and charges also. Okay, so that is why, you know, we show them in double, you know, in these, like that, you know, you show them in the square brackets and then -3 charge outside, but it's okay to show them like this also. So, all right, so that's one thing. Now comes the formal charge, and I will just finish this formal charge. How do you know that this is even correct? How do you know that this electron is actually, that this particular atom is taking a negative charge? So this is what it is. Okay. Formal charge, the formula is the, I think it's the total number of bonding electrons minus the total number of valence electrons minus the number of non-bonding electrons minus half the bonding electrons. So write the formula. So formal charge formula is the total number of valence electrons. Total number of valence electrons minus the number of non-bonding electrons, number of non-bonding electrons. Non-bonding electrons. Non-bonding electrons are the lone pairs. Okay, minus half the number of bonding electrons. Okay, bonding electrons, and that is going to be the formal charge on that atom. Formal charge on that atom. So how are you going to do this? You're going to say, you're going to take this as PO4 3 negative. Okay, now here what you're going to do. P, you're going to label these oxygens. A, oxygen B, oxygen C, and this oxygen is D. Okay. Label the oxygens as A, B, C, and D. Okay. And now you put the D is, this is double bond. And here 1, 2, 3, 4. This guy is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. Now, let's just label these with another color. Okay. A, B, C, and D. Okay. So phosphorus, oxygen A, oxygen B, oxygen C, and oxygen D. Are we really sure that this oxygen has a negative charge? This one is having a negative charge. This one is having a negative charge. This is how we find out. So let's do this. Just do this here. Okay. So total valence electrons. Phosphorus is 5. Oxygen is 6. This oxygen is 6. All oxygens will have 6 valence electrons. Now, on phosphorus, what was that? Non-bonding electrons. Do you see any lone pair? Lone pairs? Lone pair. On phosphorus, do you see any lone pairs on phosphorus? Or in the total number, 1 second, 4 non-bonding electrons. Yeah. So lone pair means the, let's just put it here, non-bonding electrons. On phosphorus, 0, right? But on the oxygen A, how many? 1, 2, non-bonding, 1, 2, 3, 4, 5, 6. On the other one, on other oxygen is also 6. The third oxygen C is also 6. The D, oxygen has only 4. You see that? Yeah. Yeah. Anytime it will be double bonded, it will be only 4. Then comes the half the number of bonding electrons. So in the case of the first one, phosphorus is how much? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So phosphorus has 5, half the number of bonded. So half would be like, just 1 electron basically that's being shared. So you're just using that one. Okay, oxygen A is only 1. Oxygen, so this is minus. Remember, this is minus, this is minus, this is minus, this is minus, 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 and then, okay. So the next one, B, also is 1. The next C is also 1. The D is 2. Okay, so now you see what are the charges. Where are the charges in reality? So you see, this would be phosphorus, no charge on the phosphorus. You see that? Second is 6 plus 6 minus 6, so only minus 1 charge left. Minus 1 left, right? When you subtract these, this is also minus 1. And the other one is 0. So this means that this oxygen is this with the 0 charge. And the other ones are oxygen A, oxygen B, oxygen C. We confirm it. Minus 1 charges here. And phosphorus is in the middle. Phosphorus is here, 0 charge. So the charge is on the oxygens. Okay, guys? Sorry, this was this is a lot of things in this, but we covered most of it. Okay, guys, so the rest is all practice, but it's very important you guys get the practice on drawing the Lewis structures because hybridization is all that, okay? And if you don't understand something, you ask me. No worries, I'll help you. And I'm going to post some more, videos so you can see, but I will be making, here's the thing, guys, one thing. Pay attention, everyone pay attention. Remember when we first started, first day of the class, when we do the course orientation? Okay, Chelsea, just a minute. When I did the course orientation, I already told you, we have so many chapters and we have only certain number of weeks and by the grace of God, November and December is just like, December is nothing for you guys. You're done by the time December comes. The course is finished. I don't teach anything new in December. Now comes November. Thursday is the Veterans holiday, so we are not meeting. Then comes another Thursday, which is our Thanksgiving holiday. Then we are not meeting. You see that? And then on one of the Thursdays and one of the Tuesdays, I think in November 2 is the exam, or one of the days, I'm not exactly remembering. So you see how many meeting days are left in November then? You see that? So that is why I'm telling you, if I'm really trying to do my best to cover a lot of things, so you guys, get the best of everything. But in case something is I'm unable to cover, I'm going to make the video. So this part, this is really easy. It's not that hard. It's like really easy, but I still have to do it. So I'm going to make these videos on bond energy and lattice energy. So that you should watch and make notes of it. Okay. Bond energy and lattice energy. And if you don't understand something, then yeah, no worries. I can, we can cover that in some other review or something. We'll figure it out. But so watch the videos. I will make them over the weekend, bond energy, lattice energy, and then the rest of it is just practice. Okay. All right, guys. Any questions? So yeah, so Chelsea, you was asking, can you please explain half bonding? How did you get those numbers? Half is like half of bonding. So you see this, how many electrons are bonding here? 2 electrons are bonding, right? Half of bonding electrons would be just 1, right? So same is the case with this one over here. Half of bonding, these are 2 electrons are bonding with oxygen and phosphorus. So half of 2 is 1. So that's how you get 1. Okay, got it? Okay, good. All right. All right, guys. Okay, bye, guys. Thanks for participating.